Hi everyone, my name is Venkatesh Chilapur. In this video, I am going to demonstrate the working of the shipping example on peak current mode control from the embedded coder TI-C2000 hardware support package. Agenda: I will first provide an overview of the peak current mode control. Next, I will discuss on the implementation details of the shipping example DC-DC buck converter using peak current mode control that is provided as part of the embedded coder TI-C2000 support package. Finally, I will run the shipping example on an actual hardware setup and view the results. Peak current mode control is the widely used control strategy for DC-DC converters. This control strategy provides stable output independent of input fluctuations, inherent short circuit protection, cycle by cycle current limiting, among other advantages, and is more suitable for mission critical applications. The current mode control features a dual loop control circuit, a voltage loop, and a current loop within the voltage loop. This current loop would sense the switch current and compare it to a threshold level defined by the voltage controller. The switch is turned off when the inductor current reaches the input level of the voltage controller. This PWM trip action, which turns off the switch at the peak inductor current, is able to generate a duty cycle for the given voltage set point. Now let's touch upon the operation of peak current on a TI-C2000 controller. Initially, the duty is set to 100% and the PWM is driven high. The output voltage of the converter that is applied to a sampling divider network is connected to the C2000 controller ADC. The voltage is sampled and converted to a digital value. A digital reference is subtracted from the digital value and the resulting error value is used as an input to the digital controller. A scaled output is used as an input to the DAC connected to the comparator's inverting input. The non-inverting input is connected to the current sense transformer. The output of the comparator will change state when the inductor current reaches the level of the voltage on the DAC output. This causes a cycle by cycle trip event to occur within the PWM module. The PWM signal will be low for the rest of the switching period. Now let's get into the details of the shipping example and see how the model is set up to achieve the peak current mode control for a DC-DC buck converter. I recommend to go through the documentation page of the shipping example that provides an overview of the design and implementation details. This example is implemented on a TI-C2000 F280049C launchpad and TI buck converter booster pack. As discussed before, we need to configure the comparator, EWM and ADC subsystem as part of the peak current control. We have also made use of the CLA to run the control loop. Next, we talk about the prerequisites for the MathWorks products that needs to be installed to run the example, followed by required hardware and a table for hardware pin connections. We have two model files as part of this example. The target model file named F280049C DC-DC buck peak current mode control runs on the TI-C2000 controller, while the model named C2000 host read peak current mode control runs on the host machine. The host model communicates to the target model over the SCI serial link and is used for parameter tuning and signal logging. From the host model, one can read the buck converter output voltage, drive a new voltage set point, tune gain parameters, etc. and the target model would adapt to these requests. Before getting further into the documentation, let's get a quick overview of the target model. The model executes at a sampling frequency of 200 kHz. This is the rate at which the peak current loop executes. We configure the EWM module to generate a start of conversion event in ADC at this switching frequency. The end of conversion interrupt from ADC would start a task in CLA to execute the control loop. Given the high sampling frequency of 200 kHz and also the need to support the two model approach for host target communication, the CPU bandwidth was offloaded to CLA to execute the control loop. This enabled the CPU to achieve the host target communication at such high sampling frequency. So, while the CLA is running the control loop, the CPU is able to send and receive serial data with the host model. After the control logic computes the new peak current value, the CLA interrupts the CPU, and within this interrupt, we are able to program the new DAC value for the comparator, which is basically the new actuation value based on the error in the system. Now let's get back to the documentation and understand the configurations in more detail. Next part of the documentation describes the details of the configuration, starting with the CMPSS subsystem. Comparator high of the CMPSS1 is used for cycle-by-cycle trip of the EPWM module as part of the peak current mode control. Comparator low of the CMPSS1 is used to implement a redundant overcurrent protection scheme, and this output is configured for one short trip in the EPWM module. One needs to clear this trip flag to enable the peak current operation in an overcurrent condition. In the EPWM configurations, the timer period is set to a value such that we attain a switching frequency of 200 kHz. This is the rate at which the peak current mode control is executed. We also want to start the ADC start of conversion event well before the next PWM cycle to update the peak current value. Other configurations in the EPWM module include the trip zone configurations, the deadband configuration, action qualifier configuration, and digital compare configurations. Now let's touch upon the configuration that enables the execution of the digital control algorithm. EPWM triggers the ADC start of conversion at a switching frequency of 200 kHz to sample the output voltage. ADC end of conversion interrupt starts a CLA task that executes the digital control algorithm to compute the actuation value or the new peak current threshold depending upon the error in the system. The end of CLA task gives a CLA interrupt to CPU in which the computed new peak current value is programmed into the CMPSS stack. Now, having understood the design and the operation principle of the peak current mode control, now let us run the example model on the F280049 launchpad and view results. Refer to the hardware connection section in this documentation page above on the details of connection between launchpad and the buck converter booster pack. The launchpad is powered by a micro USB cable connected to the host machine. The booster pack is powered by a DC power supply with the input voltage of 9 volts. Ensure the SWN switch is in the off position. Now it's time to deploy the target model onto the launchpad. Ensure to turn the SWN switch to on position on the buck converter booster pack before doing it. Open the target model and press Ctrl+B. This should build the model and download the same to the controller and launch it. Once the target model is successfully deployed, you should see a red LED blinking on the hardware board indicating that the code is running. Now let's open the host model and try to configure the serial blocks for the COM port number. You should open a device manager and look for the COM port number corresponding to the user UART as shown in this picture. Configure the serial blocks for this COM port number and try to run this model. As you can see, my voltage request is for 2 volts and I am getting the feedback value from the buck converter stage that its output has reached the requested value of 2 volts. Using the host model, I can communicate to the target model and basically change the value for the voltage set point, change the gain parameters, change the value of the overcurrent limit, and enable or disable the active load. Now let's enable and disable the active load to study the effect of abrupt changes in the load circuit. As can be noticed, when the active load is enabled, there is a dip in the output voltage, but the controller is able to recover back to the set point. Similarly, when the active load is disabled, there is an overshoot and the controller is again able to recover back to the reference voltage set point. We will also quickly try to change the voltage request and see if the controller is able to respond to the new voltage set point. Finally, let's touch upon the overcurrent limit parameter. By default, this parameter is set to a high threshold of 5.2 amps. When we are operating under normal condition and regulating an output voltage of 2 volts, we will never see an output current of 5.2 amps. Hence, this overcurrent limit is not detected. But if we reduce this threshold for testing purposes, then we should be able to see the output getting tripped. As noted before, this is an one-shot trip and we must clear the trip flag to re-enable the output. As noted, the lower current threshold has made the output getting tripped. To re-enable the output, there is a specific sequence. First, set back the high current threshold value. Request the voltage set point again. As you can see, we have again recovered the output and we have reached the voltage set point back to 2 volts. At the end of the documentation, there is a troubleshooting section that you may be interested in if you are not getting the results as expected. I hope this video was able to give you a good overview of this shipping example. Thank you for your time.